Okay, so welcome to part 4 of the video on expectation values. Okay, so in this video we're going to discuss the other property of the expectation value function, which is linearity. Well, it's the second part of linearity. So, this is the setup we have. We have our abstract probability space here, which has a sample space, a set of events, and a probability measure defined on it. We then have two random variables, let's say x and y, which map this probability space onto some probability space with outcomes elements of the real numbers. So here we go. Then what we want to do is we want to define x plus y to be another random variable defined on here, which is going to be defined by, it's going to take x plus y of some element s, where s is an element of this sample space up here. So s is any element of omega up here, so s is some outcome here. It's going to take it onto x of s plus y of s. So for any outcome in your sample space up here, there is a real number ascribed to it, so x ascribes a real number to it, and also y ascribes a real number to it. So basically I'm making a new function, which is just going to take any value in here to the value this one takes, plus the value this one takes. So that's well defined because every outcome indeed has an x and a y value, and every outcome has only one x and only one y value, therefore it's going to have only one x plus y value. Okay, so what we want to do is we want to show that this new random variable is in fact a random variable. And so firstly, let's note that it does indeed map this abstract probability space onto a set of real numbers. So it gives every outcome a real number. But that's not the only axiom it needs to obey to be a probability space. That's not the only axiom it needs to obey to be a random variable. It also needs to obey the property that if I take any event in this probability space, that the inverse image of that is an event in this abstract probability space. Okay, so the way we can check that is we note that this is a discrete random variable. So we're only working with discrete random variables at the moment. And it will be a discrete random variable as long as x and y are both discrete random variables. So if these two are discrete random variables, this one is also a discrete random variable. And the reason is that if these two are both countable sets, then the absolute size, the absolute maximum size this one could possibly be is the Cartesian product of this one with this one. And if you recall from a basic course on well, I don't know, numbers and sets, the Cartesian product of two countable sets is also countable, and the reason is that if you build an array like this, so you have every number of this set up here, and you have every number of this set down here, then you can combine them all up in this great big array here, and then you can count them as follows, like this. So just go down the list like that, and every element in this array will eventually be counted as your count. So therefore, it is indeed countable, and it is you can put it in bijection with the natural numbers. Okay, that's why if these two are discrete random variables, this one will also be a discrete random variable. Now, if it is a discrete random variable, then we know that if you take any outcome in here, then, so for instance, let's just say A is a real number, and it's an outcome in this abstract probability space. Then if we put A in a set by itself, that is an event, that is an element of the set of events. So let's say f prime, it's a set of it's an element of the set of events here. So any event in this sample space can be written as the countable disjoint union of these unitary sets. So if I take an event E, it is equal to the disjoint union of all the A is an element of E, of these sets, singleton sets containing A. Okay, and then by well, just by basic set theory, if we want to take the inverse image of this, x plus y inverse of E, it's going to be equal to x plus y inverse of this disjoint union, A is an element of E, of these singleton sets containing A, and then this can sort of be commutes with the property of taking a union, because if you're taking the inverse image of this one, you'll get a little bit over here. If you take the inverse image of this one, you'll get a little bit over here. So it's the same as this. If you union them all together first and then take the inverse image of that, it's the same as taking the inverse image of each little bit and then unioning them all together. So it's equal to the union. A is an element of E of x plus y inverse of A. So if x plus y inverse of A is an element of the set of events, then it would imply that for any element, this union is a set of events. If this is true, for all A is an element of, let's call this probability space omega star. So for all A is an element of omega prime, rather, then that would imply that for all E is an element of f prime, the inverse image of E is an element of f. The reason being that if all of these are elements of f, then every set E can be expressed as this union like this. So the inverse image of E can be expressed like this, and if all of these are elements of f, then the union of them is also, then a countable union of them is also an element of f by the basic axioms of sigma algebras. Okay, so that would prove the property what we tried to prove. Oh, that just proves that all we need to check is, is that x plus y inverse of a singleton set A is an element of f. So what is the inverse image of a singleton set A? So if you've got this set A, well, this outcome A, in its own little set considered an event, what is the inverse image of that? It's all the points in this abstract probability space up here which were mapped onto A, i.e. where x plus y, so all the points in S such that x of S plus y of S were equal to A. Okay, so what you can do is you can use the law of total probability here. We can, if I draw another picture, here's our abstract probability space. We can split up the probability space into the classes of elements which were all mapped onto a single x value. So split it up. So all of the elements in this one were mapped onto a x of any s in here. So if S is an element of here, it was mapped onto a specific x value, so let's just say x1. In here it was mapped onto another x value, x2. So we can split it up into little sets of elements of the sample space which were all mapped onto the same x value, okay? And then what we can do is we can apply the law of total probability, because this forms a partition of this overall set. So we can say that we're not really applying the law of total probability here, we're applying just logic. We're saying if you get this x value, what y value would you have to get to get x plus y to be equal to A? So what y value would you have to get successfully onto A?